Hello everyone, welcome to the new video of material science. Today we will discuss resilience and toughness. The two mechanical property, resilience and toughness. What is resilience and what is toughness? Let us see. So resilience is what? The capacity of a material to absorb energy when it is deformed elastically. You see here we have the stress strain curve and we discussed this a lot in the previous videos. We have the elastic region, we have the plastic region. When we are deforming the material, it absorbs energy, right? But the energy absorbed by the material till elastic limit, till the proportional limit here is known as a resilience. This is that capacity of the material is known as resilience. And this energy can be recovered once we remove the force. Like the energy from here, we have the elastic, it starts from here, here is the elastic point, right? So in this region, whatever energy the material is absorbing is known as that capacity of the material is known as resilience, right? This is here at what? Here we have the yield strength and we have the yield strain here at this point, right? So the capacity of a material to absorb energy when it is deformed elastically is known as a resilience. Now the property associated with resilience is we previously we discussed stiffness, right? And the property associated with stiffness was modulus of elasticity or Young's modulus, right? Here the property associated with resilience we call it modulus of resilience, modulus of resilience, and we represent that one with UR. This UR, how we can find? This is modulus of resilience. As we say that this is the energy absorbed by the material. So what we can do, if we integrate this curve, right, with respect to the strain, we can get the modulus of resilience. How? This UR is equal to integral from 0 to yield strain, right, epsilon y, and if we integrate stress with respect to strain, we will get this area. And this area will give us the energy absorbed by the material in this region till elastic point. But let us say if we take this one, that this line, usually it is not a straight line, but if we assume that it is completely straight line, then from here to here, this is one right angle triangle. And the area which is inside here, it is actually the area of that triangle, right? So area of triangle is equal to what? We can also say that this mu, the UR is equal to half base times height. So base is what? This epsilon y and height is sigma y. So epsilon y into sigma y, half base times height. This will give you the modulus of resilience also, right? Now in this formula what we can do? We can write that UR is equal to half sigma epsilon y, but we know that epsilon y is what? This is strain, right? And strain is equal to sigma yield divided by Young's modulus. So just substitute this one here. What we will get? We will get half sigma, this is sigma y, right? Sigma y, and instead of epsilon y, we put sigma y divided by Young's modulus. So we can write this one also, that it is half sigma y square divided by Young's modulus. This is also resilience. So to find the resilience, you can use this formula, you can use this formula, or you can use this formula. You will get resilience from this. Now resilience is what? Energy absorbed by the material till the elastic point. Now from here the toughness is coming. Then the new thing, toughness we have to discuss. Now toughness is the same concept of resilience, same concept like resilience, but toughness is the energy absorbed by the material till the fracture point, not till the elastic point, till the fracture point. So look, here we have this is the proportional limit, then the material goes here and somewhere here, let us say the material fracture. Now here we have the strain somewhere, this is we call it fracture strain, we call it fracture strain. So the area under the curve, the total curve, right, Let me just erase this one. Now the area under this total curve from here to here, let us say we have fracture and we have the epsilon f, the fracture strain. So what we will do, we find the area, this total area, all from 0 to fracture strain. This will give us the toughness. So toughness is the energy absorbed by the material till fracture point, right. Now within the toughness there is resilience also, but resilience is that energy which we can recover, but toughness is the energy which we can recover plus which we cannot recover, which is in the plastic region, right. So look here, for this if we have different curve, this is one curve, and if we have for the brittle material, this is let us say another curve. So brittle material usually fracture happens here, right. So till fracture the energy absorbed by this the material is this much, which is very less. So this is not tough material. This material is tough material as compared to like this, right. And if we have another material, let us say where it is too much ductile, like from here and it goes here somewhere, here the fracture occur. Again you will see the plastic region is more, but we have to see whether the area under this curve is more or under this curve is more. So usually for polymer we will see this type of curve, very low Young's modulus, and then we see the plastic deformation a lot. But that does not mean, this is usually for plastic. For metal we have this, and here this is mainly for ceramics we see these types of curve. So metals are the most ductile and tough material as compared to polymer and ceramics. Polymer is more like we can say ductile, but it is not tough because the energy absorbed by that polymer is very less. Clear? So this is the concept of toughness. Now toughness, why we need toughness? Just few examples of toughness. If we have a material, this material, if you hit it from this side, so if it absorb energy, very less amount of energy will be transferred here, right. So let us say your car, the front of your car, this is let us say your car, right, and you are going in here, like this is the front of your car, right. Now if it hits something here and the passenger is here, if the material from here to here in this region, if it is tough material, so even if it hits something, the energy will be absorbed here in this region, whatever material is here, and very less amount of energy will be transferred to the passenger or driver, right. But if this material is not tough, whatever energy is coming from here, all energy will be transferred here, and the driver will be in great trouble. So we need to use tough material here. And now you might have seen the bulletproof screen, the bulletproof jackets and all these things. Why it is bulletproof? Because the energy which is coming, the kinetic energy in the bullet is absorbed by that material and it is not passing from the material. Why? Because the material is too much tough. So if we have that type of tough material, even we can block the bullet. And now the concept, the new concept is to have smart structure to increase the toughness of the material. Not even the material, like it is the material property also, but with structure also we can vary the toughness. How? If we make, let's suppose the structure, you might have seen nowadays this honeycomb type structure, right. We have this type of structure. You make any material, just some structure like this. Now this material, there are cavities, these cavities are there. If you hit this material from here, what will happen? The energy which you are giving here, will it be transferred to this point immediately? No. The energy will be utilized to compress this cavity, compress this cavity, this cavity, this cavity, and then a lot of energy will be absorbed here, and at the end some energy will be transferred here. So means with smart structure we can also increase the toughness of the material. Not only from material to material it varies, in structure also it changes the toughness. Now with resilience and toughness, both we are saying it is area under the curve, right. So, if it is area under the curve, we say it is half stress times strain, let us say, right, stress times strain. So, if it is energy absorbed by the material, then this unit should be energy unit, right. But here whatever unit you are getting, this half is constant, strain does not have any unit, and for the stress, what is the unit? Newton per meter square, but Newton per meter square is not energy. So, how this is energy then? So, what we do in that case, if we multiply this with meter and divide by meter, we will get what? Newton meter divided by meter cube, right. So, Newton meter divided by meter cube, Newton meter is what? Joule, we can say joule per meter cube. So, joule is energy. The energy absorbed in a unit volume is, we can say that this is resilience or toughness. If it is still proportional limit, it is resilience. If it is still fracture point, it is toughness. So, this is the unit energy absorbed by unit volume, joule per meter cube, and this is coming using this process we can get this energy. So, this is all about resilience and toughness. I hope you understood.